This is a picture of a killer that takes the lives of coal miners every year. A killer that creeps into the lungs of its victims, slowly and insidiously, until after a span of 10, 15, or 20 years, the miner discovers that the contamination in his lungs is so great that he is no longer able to work. This contamination or disease of the lungs is called coal workers' pneumoconiosis, sometimes referred to as black lung. Pneumoconiosis is caused by coal dust particles so small that there is no present technology available to remove them. Here they are shown greatly magnified on the screen of a microprojector. They are so minute that when inhaled into the smallest air spaces of the miner's lungs, they accumulate there and prevent normal respiration or breathing. In many cases, a miner will be ignorant of his condition for many years, until the physical symptoms first appear. By then, it is too late, for all too frequently, the disease can lead to death. Since there is no known cure for the disease, the Bureau of Mines is dealing with technical means to control its cause. The Coal Mine Health and Safety Act of 1969 requires the Bureau to enforce established acceptable limits of respirable dust. In order to help meet this requirement, the Bureau conducts and sponsors research to improve the technology for controlling respirable coal dust. In April 1968, a study of the occurrence of dust in various underground mining operations was initiated. The criteria for the mines selected were, first, they must employ more than 20 men underground. And second, the operational production expectancy of the mine must be in excess of 10 years. The purpose of the study was to determine the level of dust associated with various coal mining methods, ventilating efficiency, types of coal, and specific mining jobs. This information was then used to develop methods to measure coal mine dust and to promulgate hygienic standards. Three of the instruments used in the survey to sample dust-laden air were the MRE, England's Mine Research Establishment instrument, the midget impinger, and the personal sampler. The personal sampler samples air from the worker's breathing zone continuously throughout the working shift. The mine atmosphere is drawn through the device by a portable, battery-operated diaphragm pump. Due to its design and weight, the MRE instrument is usually employed as an instrument to measure dust concentrations in the general environment of the workers. Both the MRE and the personal sampler are designated to operate over the entire work shift and are usually employed on a portal-to-portal basis. Here, a member of the Bureau of Mines dust sampling crew uses a midget impinger to collect dust samples. These will be assessed and correlated with the other samples collected to determine the dust concentrations comprising this mine environment. Under the new Health and Safety Act, either the MRE or equivalent device, such as the personal sampler instrument, can be used to measure the concentrations of respirable dust. The data obtained from the mines studied indicated the relative levels of dust concentrations and pinpointed dust control problems typical to most of the underground coal mining industry. The findings showed that, 1, a significant portion of the underground work occupations had exposures in excess of the respirable dust standard contained in the Act. This standard requires each operator to continuously maintain the respirable dust content in the mine atmosphere to which any miner is exposed at or below 3.0, or with a permit of non-compliance at 4.5 milligrams of respirable dust per cubic meter of air sampled. 2, that mining machine operators and helpers generally had the highest dust exposure. 3, that control measures in general use were limited to face ventilation and use of water sprays. And 4, that some mines were using dust-laden air for intake ventilation. From these findings, it was apparent that hygienic standards for respirable dust were badly needed, and that engineering control methods would have to be applied to reduce the dust concentrations to comparatively safe levels. Experiments since initiated by the Bureau have demonstrated the effectiveness of ventilation for controlling concentration of respirable coal mine dust. Experiments in 5 of these mines showed that by using high-pressure exhaust fans as auxiliary ventilation units to increase air volume and velocity, and by controlling the airflow pattern, face-generated dust could be effectively reduced. All of these mines employed continuous mining machines on mine development work. Additional data was obtained from face mining operations in 2 other mines using similar ventilation systems. An airflow velocity approaching 100 feet per minute across the entry reduced the concentration of respirable dust by factors as great as 6.4. In almost all of the mines studied, where auxiliary ventilation systems were used, the face-generated dust concentrations were reduced to below 3 milligrams per cubic meter of air measured. This was within the initial respirable dust standard established by the new coal mine law. In 2 other cases, the total respirable dust was above the approved level because the dust content of the intake air approached or surpassed the recommended standard. In some mines, depending upon the type of coal being mined and other dust control methods in use, it was possible to obtain concentrations of less than 2 milligrams per cubic meter of air measured. This is the dust standard to become effective December 30th, 1972. Although it has been established that face operations are the principal source of coal dust generation, other dust contaminant sources must be considered in overall dust control plans. These are conveyor transfer points, belt transportation systems, uncovered coal trips, open coal dumping stations, and roadways. Industrial emphasis is largely directed to maximum production per unit of manpower. However, since the rate of dust generation is directly related to the rate of coal removal, manufacturers of coal-producing machines must provide more effective dust controls in their equipment design. Factors in the design of continuous mining machines that can aid in minimizing dust production are the number of bits, size, spacing and angle of impact, cutting speed, or rate of power application, and the utilization of special bits with built-in water jets that direct a spray on the coal face while it is being cut. Water is widely used in the mining industry as a dust allaying agent. Combined with face ventilation, it is today the most common means employed for the control of airborne dust concentrations. Water sprays on mining machines are beneficial as a suppression device for total airborne dust, and in wetting the coal for handling and transporting. In Europe, where longwall mining is the established method of coal extraction, water infusion is often used as a dust control technique. This is not a common practice in the United States, and the few reported applications have so far shown only limited success. In this infusion operation, a hollow rod with a seal on the exterior end is inserted into a hole drilled into the face. Water under pressure is injected into the coal bed through the long drill hole. The liquid penetrates the coal along fractures and cracks. The high infusion pressure sometimes partially fractures the coal, which provides methane drainage and assists subsequent mining operations. Further study and controlled experiments are needed if this method is to become effective for American coal mines. In some instances, the dust suppression efficiency of water infusion can be improved by means of wetting agents or salt solutions. Investigations are being made to evaluate the effectiveness of certain chemicals that may increase the wettability of coal dust. High expansion detergent foam is also being studied. The foaming agent is a synthetic detergent which is fed into the water supply line from a tank pressurized with nitrogen. Although there was noticeable improvement compared to water alone, certain problems encountered were flooding of the work area, foam accumulation, and the need for a suitable delivery system to discharge foam at the face. The use of dust collecting equipment at points of dust generation is another approach to dust control. In drilling operations, hollow drill rods through which dust can be withdrawn have been developed. These remove the dust before it is disseminated into the air. Also, coal drills provided with water jackets installed at the drive end of hollow steel augers are in use. Water passes through the auger and discharges into the hole around the drill bit where the dust is generated. This not only washes or flushes the cuttings and dust away, but also helps cool the drilling bit. There are various kinds of dust collectors available that represent possible solutions to the dust control problem. However, due to limited space and high power requirements in most coal mines, further research and development will be needed to adapt them for underground use. The use of personal protective equipment, such as respirators, has not been favorably accepted by the industrial hygienist or the worker as a protective measure for a full working shift. Their use has been limited to temporary periods and for emergency situations. Their unacceptability is based on discomfort, interference with verbal communications, and the principle that the control of the worker's environment should be the first line of defense in any health conservation plan. Life support systems have been developed that provide the worker with an independent uncontaminated air source using either a liquid air system or a supply of filtered ambient air. Some are similar to those which the astronauts wear. These systems are based on the mobility required by the wearer and the level of enclosure or space in which he must work. However, further studies and testing of life support systems are needed to determine their possible adaptability to underground mining environments. At the present time, all practical and more immediate solutions to the dust problem seem to point toward control by ventilation or water, or a combination of both. The suppression of respirable dust to prevent pneumoconiosis is now recognized as vital to the reduction of both the human costs and production costs of coal mining. Considerable progress has been made in this country in man-hour productivity. So much so that we can proudly load coal in West Virginia, send it to an eastern seaport via train, to Europe via ocean freight, and easily undersell European competitors in their own backyards. Had similar strides been taken in coal mining health protection, the need for rehabilitation in miners' clinics such as this would be greatly reduced. But the final objective, to protect the health of the coal miner, can be reached. To meet this objective is the joint responsibility of management and labor. Management can do their share by providing the necessary equipment and conditions, such as respiratory and dust-allaying devices, water and ventilation. The mine worker can do his share by properly using these aids. And finally, necessary engineering technology and environmental controls to solve these problems must be provided to meet the standards set by the Federal Coal Mine Health and Safety Act of 1969. Section 201B of the Act clearly defines the purpose of the law. It states, among other things, it is the purpose of this title to provide, to the greatest extent possible, that the working conditions in each underground coal mine are sufficiently free of respirable dust concentrations in the mine atmosphere to permit each miner the opportunity to work underground during the period of his entire adult life without incurring any disability from pneumoconiosis or any other occupational-related disease. When these conditions are met, then and only then will this insidious killer have been conquered.